Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I want to talk about some new results in clustering theory. I'll be actually talking about K-means, the K-means clustering problem. Okay, so the first result is a joint work with a student of mine, Nitin Garg from IIT Delhi. So I'm going to start talking about that, and then maybe if I get time, I'll talk about the other work. Okay, so this audience already knows about the K-means clustering problem. So let me go through the basics very quickly. You're given n points in d dimensions. Okay, what you want to do is output k points, which are called the centers, such that the sum of square of the distances of each of the points to its closest center is minimized. Okay, so that means this objective function is basically minimized. So for example, you are given a two-dimensional data, and the red dots denote the given points. Then you want to output, and if k is for example 3, then you want to output these blue dots such that the sum of square of distances of each of the red dots to the closest blue dot is minimized. Okay, so the one means problem is easy. All you have to do is to just output the geometry, the centroid of the given points. Okay, but this problem becomes NP hard as soon as k becomes larger than 2. Okay, greater than or equal to 2. Okay, so there have been a whole lot of work on finding approximation algorithm for this problem, and this list is actually very huge. This is a very small, brief picture of what goes on. Okay. So many algorithms in this particular picture are quadratic time algorithms. Okay, and let me not go into the details. What I want to talk about is actually something different, not approximation algorithms, quadratic running time approximation algorithms. I want to talk about the Lloyd's algorithm first. Okay, so even though there are tons of approximation algorithms available, what is used in practice to cluster data is actually something very simple. It's a heuristic. It's called the Lloyd's algorithm, more popularly known as the K-means algorithm. What you do here is very simple. You start by picking k centers in a completely arbitrary manner. Okay, then you cluster points based on the distance of the points to its closest center. Okay, then again you find the centroid of these clusters and then shift these points to the centroids, and this repeat the process until the process stabilizes. Okay, so everybody knows about this. The problem is this algorithm is a heuristic. There are absolutely no theoretical guarantees. Okay, so this algorithm, this heuristic, might behave very badly. For example, this algorithm may get stuck in a local minima, and the quality of the solution could be arbitrarily bad, or it might take a huge amount of time to converge to something that is optimal, even close to the optimum. Okay, so let me give an example of the first problem using a very simple example. Okay. So consider this example. Okay, so these big circles denote a bunch of points. Okay, so they are uniformly distributed points between these big circles. Now you're trying to cluster these points using the Lloyd's algorithm. Okay, now suppose the Lloyd's algorithm pick these blue dots as the initial centers, 4 centers. Okay, now if you do that, the algorithm is going to get stuck in a local minimum. Okay, so this might be what the Lloyd's algorithm is going to get stuck into. Okay, and the quality of the solution could be arbitrarily bad compared to the optimal. Optimal, we know we should pick the center point in each of these 4 clusters. Okay, so now people have been trying to figure out what is the reason, how we can fix this problem in the Lloyd's algorithm, and one of the problems clearly is the choice of the initial k centers. Okay, so picking k centers initially in a totally arbitrary manner does not help, and you can end up in this kind of situation. Okay, so people have tried various heuristics. What if we just pick k centers in a random fashion? Okay, then even in that case, there are problems. You can argue that there are data sets on which, with high probability, you're going to get very bad centers. Okay, so now there have been various heuristics to deal with this issue, and one heuristic, or we can even call this an algorithm. I'll talk about the theoretical guarantees for this algorithm, which has gained prominence in the past, is the K-means plus algorithm. Okay, it's an extremely simple sampling technique. Okay, the authors call it D2 sampling, and all you do is pick k centers in the following fashion. You pick the first center from among the given points completely randomly. From then on, you pick a point to be the ith center for I greater than 1 with probability that is proportional to the square of the distance of this point to the previously chosen centers. Okay, so you have a current set of centers that defines a probability distribution, and you pick a point from this probability distribution to be the next center. Okay. So in essence what you're trying to do, what this algorithm is trying to do, is to spread the centers as far as possible. Okay. A point is less likely to be chosen as the next center if it is closer to one of the previously chosen centers. Okay, and a point is more likely to be chosen as a next center if it is far away from the previously chosen centers. So this handles the problem that we looked at in the last slide. Okay, so you're trying to spread the centers as far as possible so that you do not get into that kind of situation that we saw in the last slide. Okay, so this is a very simple heuristic. It runs in time that is proportional to n times k times d. N is the number of points, k is the number of centers that you want, d is the dimension. Okay, very simple, very nice algorithm. The great thing about this algorithm is that you have a theoretical guarantee. Arthur and Vasilevsky in 2007 showed that this k-means plus seeding algorithm, just this seeding algorithm, gives you an order log k approximation in expectation. Okay, and what you can do is, since this algorithm runs very quickly and it's very simple, you can follow this algorithm by running the Lloyd step. The Lloyd's algorithm is not going to deteriorate the solution, so what you get is sort of best of both worlds. You have a seeding algorithm that is simple, you can implement it, that gives you a constant, that gives you a theoretical guarantee, and then you run the Lloyd step, which you know works well in practice. So you sort of get best of both worlds. Okay, so now what we are going to talk about is the analysis of this k-means plus algorithm. Okay, so what I'm going to talk about is that even the simple sampling algorithm was not fully understood. There are many aspects of the algorithm that was not understood, and that is what we are trying to understand in this particular work. Okay, so let's start talking about those issues. Arthur Vasilevsky, what they did, in addition to the first result, they gave an instance on which the k-means plus algorithm gives a omega log k approximation in expectation. Okay, so they gave sort of a lower bound. Okay, so now, but an important question remains open. The question is, does the k-means plus algorithm gives a constant approximation with probability proportional to 1 over poly k? Because even in this case, I'll say the algorithm is interesting. With 1 over poly k probability, you get a constant approximation. Okay, so that is great. I can just repeat the algorithm, choose the best center, poly k times. Okay, this is something that was not well understood. Okay, and I'm going to talk about this particular question. Okay, so note that after this work, there was a couple of work, one by me, Nir, and Claire, and in parallel by Agarwal, Deshpande, and Kannan. And what they showed is that you can get a constant pseudo approximation. Okay, if you are allowed to choose more number of centers and then compare the quality of the solution with the quality of the optimal solution with respect to k centers, then you can show that you get a constant approximation. That means you can show that the k-means plus algorithm gives you a constant pseudo approximation. Okay. Now, let's go back to a particular work where this algorithm was already talked about. Note that this algorithm people have been using it for finding the initial centers for the Lloyd's algorithm. It's just that the Arthur Vasilevsky were the first ones to show that it comes along with a theoretical guarantee. Okay, so the first people, or one of the people to talk about discuss this particular algorithm was by Ostrovsky et al. And what they had shown already is that if the data is such that the ratio between the optimal solution with respect to k minus 1 centers to the optimal with respect to k centers is at least some constant, okay, Then the k-means plus plus algorithm gives a constant approximation, but with probability that is exponentially small in k. What's what is the constant c? Actually, so this particular, okay, so that I think you can remove that the order in k. It's 2 to the power minus k. You can show that the probability is 2 to the power minus k. Does that answer your question? And this constant, I don't know exactly. Okay. If yeah, I'm not sure about that. I have to think about it. Okay, sorry. Okay, but if for a constant you can show something like this. If it is greater than or equal to the constant, then at least you get a with exponentially small probability. You get a constant approximation. Okay, so now using a simple extension of ADK and AJM, we can show that the k-means plus plus algorithm gives a order 1 approximation with probability exponentially small in k. Actually, the separation condition. Let me talk about this a little bit. So why is this condition making sense when you talk about clustering? Okay. So what this condition says is that when you go from k to k minus 1 centers, there is a sudden sort of jump in the quality of the solution that you get. That means the data is sort of separable. It makes sense to talk about k clustering rather than k minus 1 clustering, right? And that was the reason why this sort of condition was, people even started studying this. Okay, so now you can, by an easy extension, you can argue that the k-means plus plus algorithm gives an order 1 approximation with probability exponentially small in k. You actually didn't need that separation condition that was studied by Ostrovsky et al. Okay, so now Brunch and Roglin in 2011, they show that there exists a data set on which the k-means plus plus algorithm gives 2 by 3 minus epsilon log k approximation only with exponentially small probability. Okay, so again, sort of a lower bound. Okay, so there exists a data set which is sort of bad for the k-means plus plus algorithm. You can get better than log k approximation only with probability exponentially small in k. Okay, so now let me just mention that their data set, the instance that they create, has the separation property of the following form: delta k minus 1 by delta k is of the form 1 plus 1 over k, something 1 over k. Okay, so it's the data was not very separable. Okay, so now what we show in this work is that if the data is such that it is separable, that means delta k minus 1 by delta k is greater than or equal to some constant d, okay, some universal constant d, then the k-means plus plus algorithm gives a constant approximation with probability 1 over k, omega 1 over k. Okay, so it sort of solves the problem that Ostrovsky et al. Sort of started. Okay, so you can view it as strengthening the result of Ostrovsky et al. They had shown that if the data is separable, then you get constant approximation with probability exponentially small in k. What we have shown is that if the data is separable, then the k-means plus plus algorithm gives a constant approximation with probability 1 over k. Okay, now the question is, what about distance measures other than squared Euclidean distance? Okay, can you talk something about that? Can you say similar things about those distance measures? Okay, so what we show is that our techniques are so simple that then the whole proof can be generalized for other distance measures. Okay, so for example, we can talk about distance measures that are approximately metric. Okay, that means there's some alpha approximate symmetry. There's some beta approximate triangle inequality where alpha and beta are some constants. For many distance measures, you can actually figure out these constants alpha and beta. Okay, For example, if you're talking about the square of the Euclidean distance, then alpha is equal to 1 and beta is equal to 2. Oh, beta is equal to half, sorry, given this scenario. Okay, so, okay, now Ackermann and Blomer had already shown that if the data is separable, then the k-means place plus based sampling algorithm gives an order 1 approximation with probability exponentially small in k. Okay, why I have changed a little bit here. Instead of saying k-means plus plus algorithm, I am saying k-means plus plus base sampling algorithm. Why? Because the distance measure has changed. But the idea remains the same. You're just sampling k centers. Okay, sample the first center uniformly at random. Second center, you choose a point to be the second center with probability or proportional to the distance of the point to its closest previously chosen center. Instead of talking about the square of the Euclidean distance, you talk about the distance, whatever distance you're talking about. Okay, so they have already shown that if the data is separable, then this algorithm, sampling algorithm, is going to give you a constant approximation with probability exponentially small in k. Okay. Now, in this work, we actually strengthen this result. We show that if the data, what we show is that this algorithm, the k-means plus plus base sampling algorithm, is going to give you constant approximation with probability exponentially small in k, even when the separation condition does not hold. The separability condition is actually not required when your probability is exponentially small in k. So you can get rid of that. Okay. And we show again that if the data is separable actually, then the sampling algorithm is going to give you a constant approximation with probability 1 over k. In addition, we require this sort of centroid property for this particular result, which essentially says that the centroid is optimal for the one median problem. Okay, so this sort of covers sort of description of what we have tried to do. What you basically try to do is to try to understand the k-means plus plus algorithm a little bit better. Okay, so but there are still some holes in our understanding, in our analysis. So before we talk about, okay, so okay, maybe I can I can talk about this. Okay, so let me give you sort of the general idea of how we go about proving this this kind of theorem. Okay, so now we use this lemma from Arthur and Vasilevitsky in a very crucial manner. So this lemma is very simple. What it says is that given any set of centers C and any optimal cluster A, given that the k-means plus plus seeding picks a point small c from A in the next iteration, the expected cost of A with respect to the new set of centers, that is C union small c, is at most constant times the optimal cost of cluster A. Okay. Given that your sampling algorithm picks a point from an optimal cluster, okay, the expected cost of this cluster A with respect to the new set of centers is going to be constant times, at most constant times, the optimal cost of just this cluster. Okay. So what this means is that if your sampling algorithm happens to pick a point from any optimal cluster, there's a good chance that the point you choose is a good point, and you will get a constant approximation with respect to that cluster. As soon as that happens, you can forget about that cluster because you already get a constant approximation. You need to worry about the remaining cluster. Okay, so in some sense, once this good event happens, so as soon as you pick a point, as soon as you sample a point from an uncovered cluster, there's a good chance that it's going to be covered, and you can forget about the cluster in the future iterations. Okay, so that is sort of the intuitive idea about where what we are going to use for our analysis. Okay, so now our result that is implicit in our result and Agarwal, Deshpande and Kannan's work is that is the following lemma. Okay, so this lemma says the following thing: the probability that a center from an uncovered cluster will be picked is at least half, unless the current set of centers already gives you a constant approximation. Okay, so if you do not happen to sample, if the probability of sampling a point from an uncovered cluster is small, okay, then you already get a constant, you already have a constant approximation with respect to the entire set, so you don't need to worry. Otherwise, there is a significant chance that you will sample a point from one of the uncovered clusters, and then you can straight away apply this particular lemma. As soon as that happens, you sample a point from an uncovered cluster, it gets covered. Okay, so if you, as soon as you put these two lemmas together, you immediately get this result. Okay, the k-means plus plus algorithm gives a constant approximation probability 2 to the power minus exponentially small in k. Okay. Now, so what is the main challenging task? So what we show is something of the following form. What we show, the main result that we show in this is, can be captured in this following lemma. We show is that given that I optimal clusters have been covered after the ith iteration, the probability that an uncovered cluster will be covered in the I plus 1th iteration looks something like this: k minus I divided by k minus I plus 1. So that if you just multiply, it becomes a telescoping product, everything cancels out, you get 1 over k. Okay, and the idea is very simple. Okay, so proving this in generality is going to be tough, involves a little bit of technicality, but getting the intuition, we can get the intuition from very simple data set. Okay, so consider this very simple data set. The simple example, all the clusters, all the optimal clusters have equal number of points. Let's say they have m points, and they have the same average radius. Okay, let's call it r. Okay, so now note that if you talk about the distance between any two centers, centroids, let's call it d. Okay, let d be the minimum of such intercentroid distance. Then the separation condition says that this d is going to be larger than or equal to some k times r times c. Okay, so this d, intuitively, let's not go into the details of the equations, but they are sort of separable. They are far apart. Okay, and if that happens, then if we compute the probability that the I plus 1th cluster is going to be covered, that will be proportional to k minus I divided by k minus I plus 1. Okay, it's a simple calculation. Some of them should not be r and d, which should be r square and d square, but for this particular example, things work out pretty nicely. Okay, and this is the basic sort of idea that that proves the theorem. Okay, now the problem, however, our understanding of the k-means plus plus algorithm is not complete still. There are various holes in our understanding. Okay, so the first thing that we don't understand is the following: all the lower bound instances that people in the past have given are all in high dimensions. Okay, so the question is, how does k-means plus plus behave for lower dimensional data? So how does it behave for 2-dimensional data, for example? Even that is not fully understood. Do we get a constant approximation with probability that is poly 1 over k, 1 over poly k, or we would not be able to get that? For separable data, we have shown it's done. Okay, so constant approximation with probability 1 over k. But if the data is not separable, we don't even understand what happens in 2D. Do we get a constant approximation with probability 1 over poly k, or we do not, or we can't? Okay, so even that simple things like that is not understood. Okay. Now, Brunch and Roglin give an instance that satisfies that the separation, the data is not very separable. Okay, so their lower bound instance satisfies that delta k minus 1 by delta k is less than or equal to 1 plus 1 over k. It's saying that the data is not very separable. They created a data instance, an instance which is not very separable. And our result holds when the data is separable. That means delta k minus 1 by delta k is greater than or equal to 1 plus c, where c is some constant, is a universal constant. It depends on alpha and beta, which is sort of the parameters for defining the approximate metric. The question is, how does the k-means plus plus algorithm behave in the middle between 1 plus 1 over k and 1 plus c? How does it behave? Is the transition nice? How does the transition look like? Okay, so that will be an interesting question to resolve. So okay, so with that, I want to switch to another result about clustering, which is a sort of joint work with Sandeep Sen and Amit Kumar at IITD. What we wanted to do in this particular work was to see this k-means plus the sampling based algorithm is very simple. Okay, it's very nice. Can we use the ideas from this simple sampling algorithm and extend it to construct 1 plus epsilon approximation algorithms for the k-means clustering problem? Okay, so that was the basic idea. Now, there are a lot of work on finding a 1 plus epsilon approximation for the k-means algorithm. Okay, and this list gives you sort of a brief picture of what has gone on in the literature. Okay, so I should comment that the algorithm that the PTAS, let me not yet call it a PTAS, let the 1 plus epsilon approximation algorithm that we gave in this work is actually not the best, okay, when you look at this particular list. Okay, so we are not trying to sell our algorithm as the best PTAS available, but sort of what is the power of the k-means plus algorithm? Okay, sort of understanding how the k-means plus algorithm can be used to find a very simple to define and simple to analyze 1 plus epsilon approximation algorithm for the problem. Okay, so let me start talking about that. Now the PTAS, most of the PTASs that were there in the previous slide have, well, it's not fair to call them complicated, but they have their own complexities. Okay, our PTAS can be described in just this slide, one slide. What we do is extremely simple. Okay, so there are some parameters at the top. What we do is the first line repeat 2 to the power k times is just probability amplification, so you can just forget about that. Okay, now after that, what you do is you pick all possible k tuples in the set p cross p cross p cross p. Okay, where p is just a number. Okay, it's n choose m. When we talk about, we're going to talk about all these parameters. Okay, so it's going to come out in the analysis. So you talk about all possible k tuples, and you do the following. You do k steps in iterated fashion. Okay, so in the first step you pick s of n points using D2 sampling. You just pick a bunch of points using D2 sampling. Okay, and then you consider the SIth subset, where you can just order the subsets of a particular set, and you consider the SIth one subset, and then you just consider m of t, where m of t denotes the mean of the points in t. Just take the centroid. Just take the centroid of all the points that you of that particular subset. That becomes your first center. Now you have one center defined. You again sample a lot of points using D2 sampling with respect to the center that you have chosen in the previous round. Now consider the S2th subset. Take a subset of points, this subset of points, calculate the centroid, that becomes your second center. Repeat this procedure to get the k centers. Okay, and you output the best one that you could get. Okay, so the main result, okay, so maybe talking about this algorithm is not going to be helpful. Maybe we can straight away dive into the analysis, and the algorithm can be quickly derived, reconstructed when you see the analysis. Okay, so the main result with respect to this algorithm is that given a k epsilon separable data, the above PTAS runs in time n times d times 2 to the power k times 2 to the power k over epsilon. Okay.
Didn't you take all subsets of cardinality 1 over epsilon, you said?
Yes.
But wouldn't that give you n to the 1 over epsilon already?
No, but it's n is equal to k by epsilon
So
cube.
out of the big n.
Out of the big n.
All subsets.
All subsets.
And the big n is picked at random from.
Right. Using D2 sampling. Those many number of points using D2
And
sampling.
you're running k plus plus on only the points in C, only the centroids.
Only the, yes.
So k plus plus is not going to stick to data points anymore, right? It's going to give you non-data points, averages.
Well, you sample a lot of points using due to sampling.
But you found their averages. CM is the center.
Yeah, you take their average and put it as a center. You don't pick any one of the centers. You take a lot of points, consider a subset. Actually, you're considering all subsets, all possible subsets. You take the average, and that becomes your new center. Okay. So now, what do I mean by K epsilon separability?
You need separability for this result? Assume separability.
I'm going to show a result which does not assume any separability. Okay. So let me talk about separability. What do I mean by separability? We already talked about this actually. A set of points X is said to be K epsilon separable if the following condition holds: delta K minus 1 divided by delta K is at least 1 plus epsilon. Okay, that is my definition of K epsilon separability. Okay, so using this result, the previous result that I showed, we can generalize this and get rid of the separability condition in the following fashion. We can show that our algorithm is a PTAS for any, I'm talking about PTAS where K is a constant, so don't mind that. Okay, so our algorithm is a 1 plus epsilon approximation for any data set that has running time and has a running time of order 2 to the power, it should be 2 to the power K square over epsilon. So if you remove the separability condition, the constant in the exponent, the parameters in the exponent become a little bit worse. Okay, so the proof sketch is very simple. So deriving this main general result from the result that we saw in the previous slide is very simple. If the data is not K by, say, epsilon by 1 plus epsilon by 2K separable, then solving the I means problem for appropriate I is going to give you the solution to the K means problem. Otherwise, we solve the K means problem. Okay, so it's just playing around with the appropriate epsilon. Okay, so we should just concentrate on this result that if you are given a K epsilon separable data, then you get a 1 plus epsilon approximation in running time 2 to the power K over epsilon. Okay, so let me try to give you a proof sketch. The crucial lemma that we use to get to show that it gives you a 1 plus epsilon approximation is this lemma by Inaba et al. This lemma says something very simple. So let S be a set of m points, okay, sampled independently from any given set of points X uniformly at random. Okay. Then for any delta greater than 1 or greater than 0, the following condition is going to hold with probability at least 1 minus delta. The optimal solution with respect to just one center, okay, is clearly for the K-means for the K-means problem. We know that is going to be exactly equal to delta of mx comma x, right? The centroid gives you the optimal answer, right? That is at most 1 plus 1 by delta m times the cost of the given points with respect to the average taken over points in S. Okay, so I can depict this in a nice picture over here. You're given these red dots, okay, that is your input data set. Okay, now m of p, actually should be m of x, is the centroid of all these given points. Okay, that is going to give you the optimal one means objective function, right? That is going to optimize the one means objective function. So give the optimal answer. Now you sample a subset of m points, okay, and you take the average of these points in the subset. Suppose that gives you this m of s. Okay. What this is saying is that they are not going to be very far off as far as the quality of the solution is concerned.
Is that an s at the end or is it x? Because delta of mxx is the least, right?
Right.
Why would it be ever greater than c?
Oh, sorry. I think I've
That might be an s.
yeah.
Or it might be 1 minus. No, it can't be 1 minus.
Wait a minute. Okay.
Well, possible.
I think I have to switch the inequality. It should be it actually should be the other way.
That's more like.
Yeah.
So ms comes.
Yeah. There's no negative sign. So it's positive. Okay. Yeah, sorry for this typo. Okay. Okay. So let's talk about the general idea for the analysis. Okay. So what we can show, suppose we have a very simple scenario. Okay. So we have k is equal to 4. We are talking about two-dimensional data, and we have these 4 optimal clusters. Okay. Suppose we sample m points uniformly at random from the given points. Okay. Then with good probability we are going to get at least m by 2k points from the largest cluster. Okay. So now if we sample a set S of size k by epsilon randomly from X and consider all possible subsets T of size 1 over epsilon of S, for any chosen subset T, consider MT to be the new center. Okay. Then we are going to get a 1 plus epsilon approximation with respect to the largest cluster. There's a good chance that we're going to get a 1 plus epsilon approximation with respect to the largest cluster. Okay. We have the largest cluster, we sample a lot of points. Okay. And consider all possible subsets of certain minimum size. Okay. Since we are sampling a large number of points, many of them are going to hit the largest cluster, and we are considering all possible subsets. That means that there is going to be a good subset which is going to optimize the solution with respect to the largest cluster. Okay. So this is something that we could start with, okay, using the lemma of Inaba et al. Okay. So now for the first cluster we are sort of happy. For the first cluster we get 1 plus epsilon approximation, so nothing bad with that. Suppose we try to do again the same thing with the second cluster. Again, in the second step we sample a lot of points. Many of them, since the second cluster is not too small, sufficient number of points are going to hit the second largest cluster, and we considering all possible subsets, so one of the subsets is going to be good. So you are going to get a 1 plus epsilon approximation with respect to second cluster too. Now you might end up in an issue. Okay, so the first issue that you can end up in is that now you have 2 nice centers. Okay, now but the problem is, if we again try to sample uniformly from X, then it might be unlikely that we get enough points from clusters 3 and 4, because they are very small clusters, they contain very small number of points. So uniform sampling is not going to help anymore, because now the clusters that are left sort of uncovered are very small clusters, and it might be completely unlikely that you will ever hit those clusters. And if you don't hit those clusters, picking all possible subsets and taking averages is not going to help. Okay. So what is the solution in this particular case? D2 sampling or non-uniform sampling that we have been talking about. Okay, this is exactly what the D2 sampling does. This is the problem that it solves, right? So uniform sampling is not going to help us, but if we do D2 sampling at this point of time, what it does is just boost the probability of picking a center, picking a point from clusters 3 and 4. Even though these are small, very small clusters with very small number of points, if you sample from using the D2 sampling technique, it just amplifies the probability of picking a point from our clusters, optimal clusters 3 and 4, and that's precisely what we want. Okay, so D2 sampling is going to give more weights to points in clusters 3 and 4. So it's sort of now, if we change uniform sampling by D2 sampling, then this problem is solved. You will never end up in a problem where we don't get enough points from a particular cluster. D2 sampling is always going to ensure that you get sort of points from even the smallest clusters. Okay, so now what we can actually show is the following. Okay, given a current set of centers C, okay, such that the current set of centers are nice for their respective clusters. Okay, the current set of centers that you have picked are nice with respect to those clusters from which they have been picked. Okay, that means they give a 1 plus order epsilon approximation with respect to their clusters, then either of these things happen. Either the probability of picking a point from one of the uncovered clusters is omega epsilon, or the current set of centers already gives you a 1 plus epsilon order epsilon approximation with respect to the entire set. It's something very similar that we already looked at in the one of the previous slides. Either the probability of picking a point from an uncovered cluster is not too small, or you already have 1 plus desired approximation. So you do not need to even pick any further points. Picking further points is not going to hurt you, so you may as well just pick those points. Okay. So what we have here is that either you get a 1 plus epsilon approximation, you're done, or with omega epsilon probability, you're going to pick a point. You pick a point from one of the uncovered clusters. Okay. Now what we know that if the current set of centers do not give appropriate approximation, then we will sample points from clusters 3 and 4 with non-negligible probability using D2 sampling. Now there's a second issue that we have to deal with. Okay. Now conditioned on sampling points from this optimal cluster 3, the problem is that the point may not be uniformly distributed. Okay, remember the lemma of Inaba et al. Requires this condition that you're talking about a uniform sampling of points. If you sample points uniformly from that subset and then take the average, then you will get, I'm just going to wrap and do this, okay. So then you're going to get that particular approximation. Now the problem is that, okay, you get points from these uncovered clusters, but these points may not be being sampled from the uniform distribution. Okay. So now how do you resolve this particular issue? This can be resolved in the following manner. The main idea is that if previously chosen centers are very close to this optimal cluster 3, then the points sampled from O3 are far from being uniformly distributed. Okay, so if this is the case, then you don't sample points uniformly from this optimal cluster. But if the point that you have previously chosen is far away, then you can argue that even though it is not uniformly distributed, it is close to uniformly distributed. Okay, and how do you get that? You get that from the separability condition. So the separability condition makes sure that this does not happen actually here in that particular case. And you can actually just formulate, just quantify whatever idea I'm saying in this particular slide, and you can argue is that the conditional probability of sampling a point is going to be close to what you have if you do a uniform sampling. Okay, so and this slide basically quantifies everything and says that, okay, so this is the basic idea. You sample a lot of points and talk about all possible subsets. You keep repeating it. At some point in time, you already get a 1 plus epsilon approximation, or there's a significant chance of picking or covering a new cluster, an uncovered cluster. You cover that and you keep covering it until in the end you cover everything. You get a 1 plus epsilon approximation. And if you do that, if you calculate all the parameters, it comes out to be the runtime of the problem turns out to be 2 to the power k square over epsilon. Okay, so I think I can leave the open problem section. Okay, thanks.